Dear students, in this session we will discuss about speed, size, cost with respect to memory hierarchy, what is cache memory, and what are the different types of mapping function techniques. So, from a computer user point of view, an ideal memory would be fast, large, expensive. Unfortunately, it is impossible to meet all the three of these requirements simultaneously. These speed, size, and cost are the design trade offs in memory system. That means increased speed and size are achieved at increased cost. So when we need a very high speed memory system, then automatically the cost of the system increases. So that is a big challenge in the design of computer system is to provide a sufficiently large memory with a reasonable speed at an affordable cost. As we know, the static memory, the SRAMs are very fast memory because but these chips are expensive because their basic cells have 6 transistors. So we have seen in the previous topic. So the static RAMs will be more number of transistors. So automatically it the cost also becomes high. So here, thus for the cost reason, it is impractical to build a large memory using SRAM chip. The alternative is to use a dynamic RAM chip, which have much simpler circuit, hence are much less expensive but significantly slower than SRAM. So it is less expensive, but the memory access or memory speed that is less than static RAM. The next alternative is to use a magnetic disk. So here, in the dynamic RAMs, the storage is high than the static RAMs, but is still less than what is necessary. The secondary storage, such as magnetic disk, provide a large amount of storage, but is much slower than the dynamic RAM. So this is a memory hierarchy which is shown in a pyramid structure. So as this goes down, you can see the size also it increases, the storage size. The based on the width of this, we can say that the when it goes down, when the memory goes down, memory hierarchy. So here the bottom one that is nothing but the secondary storage which is having a large storage space. So first in the memory hierarchy comes the CPU registers, which are very small memory and able to store up to 512 bytes of data, and it is very expensive and it is very fast. So the memory access time in terms of 1 nanosecond. Then the next in the level is cache memory. So it is also very fast, up to 10 nanosecond, and the storage it can store up to 12 megabytes. It is very expensive. Next, the main memory, which is nothing but a random access memory. The memory access time is 100 nanosecond. It is large compared to cache memory, so it can store up to 8 gigabytes. So it is inexpensive compared to cache memory. Then comes the hard disk and offline storage disks, that is tape drives, etc. It is very large. It can store data up to in terms of terabytes and petabytes. So it is less expensive compared to main memory and cache memory, and it is very slow. So in terms of milliseconds and in seconds, the memory access time is, so the speed is very less here. The access speed is very less here, means very high. Okay. So here it is very less. So that's why it is very fast in CPU registers and cache memory. So this is a memory hierarchy diagram which is given in your textbook. So here in the first level, we can see the CPU register, the level 1. So in the first level, the CPU registers, which is is one of the very important part of the memory hierarchy. So here the processor register at the top, it is in terms of the speed of access. But the storage wise, it provides less storage space to store the data. So processor register, it is very small memory. So the next in the level is cache memory. So here this is the fastest access is to be data held. So in the register, so when compared to processor register, the primary cache is the speed is less, but the cache memory is one of the fastest memory in the computer. It holds the copies of the instructions and data stored in a much larger memory that is provided externally. So in the second level, the hierarchy is cache memory, which is a small amount of memory that can be implemented directly on the processor chip. So the processor cache, which is implemented on the processor chip only, okay, which is inside the CP, which is located inside the CPU. So this is small and it is access time is comparable to that of the processor registers. The primary cache is referred to as the level 1 cache. So these are the level 1. Yeah, a larger and hence somewhat a slower secondary cache is placed between the primary cache and the rest of the memory. It is referred as level 2 cache. So because primary cache will be very small memory. So if we want to extend the storage of the cache, then we can go to the next level of cache memory, that is a secondary cache, L2 cache. So here the very important is as the memory hierarchy goes from top to bottom, the size of the memory storage it increases. Okay, so the storage size increases as we move towards the um, from top to bottom, and the speed increases when we goes from bottom to top in the memory hierarchy. So here the registers, the processor registers are the fast processor registers and primary cache are the fastest memory speed wise. Okay, so here and cost also it increases in the same way compared to this one speed. So here the speed also increases when we move from the bottom to top direction in the memory hierarchy. The next level is main memory, which is outside the processor CPU. So this is a larger, it provides larger memory space, but the speed is very less compared to cache memory, and it can store a huge amount of data in terms of um, megabytes and gigabytes. So speed is less and it is inexpensive. The next level is the last level is magnetic disk or secondary memory storage. It is very huge. It can store huge amount of data. The data will be in terms of terabytes and petabytes. Now it is zettabytes and all. So here the speed is very less compared to main memory. It will take much time to access the data from this magnetic disk, and it is inexpensive compared to all other memory levels. So some computers have level 3 cache of even larger size in addition to the L1 and L2 caches, and L3 cache also implemented in static RAM technology. May or may not be the same chip with the processor and the L1 and L2 cache. And these levels of cache L3 will be outside the CPU, or it may not be designed or inserted in the same chip. The main memory, this is the large memory implemented using dynamic memory components, typically assembled in memory modules such as memory modules or single line in memory modules. The main memory is much larger but significantly slower than the cache memories, as we discussed. These devices provide a very large amount of inexpensive memory, that is a secondary storage memory, and they are widely used as secondary storage in computer system. They are very slow compared to the main memory. During the program execution, the speed of memory access is of utmost importance. The key to managing the operation of the hierarchical memory system is to bring the instructions and data that are about to be used as close to the processor as possible. This is the main purpose of using cache memory. So this is called locality of reference, which data and instructions soon to be referred by the processor that should be bring near to the processor. So that is the main purpose of using cache memory. So cache is the fastest memory in the system. It is a small-sized volatile computer system that provides high speed data access to processor in terms of some nanoseconds and stores frequently used computer programs and applications and data. Cache memory, also called CPU memory, which is placed between random access memory and a computer microprocessor. It can be accessed quicker by microprocessor than regular random access memory or main memory. So this is the simple diagram to explain how exactly the cache memory works. So here the processor sends some address, the memory address from where it wants to fetch a data. It compares that address will be compared with all the stored addresses in cache memory. If that address is found, then from that address the data will be fetched and it will be sent to the processor. If that memory address is not found or not present in the cache memory, then that will be accessed from the main memory, and copy of that data which is not there in that cache memory will be one copy will be placed in the cache memory, and from there the data will be sent to the processor. So this is how it is a overview how exactly the cache memory works. As we know, the processor is much faster than the main memory. As a result, the processor has to spend much of its time waiting while instructions and data are being fetched from the main memory. So, major obstacle towards achieving a good performance is the memory access time from the main memory. Okay, the processor will take much time to access the data from the main memory, and it will be keep on waiting for the instructions and data from the main memory, so that will decrease the overall performance of a processor. The speed of the main memory cannot be increased beyond a certain point. So to overcome that, the cache memory is an architectural arrangement which makes the main memory appear faster to the processor than it really is. Cache memory is based on the property of computer programs known as locality of reference. So what is locality of reference? Locality of reference refers to a phenomenon in which a computer program tends to access same set of memory locations for a particular time period. That means analysis of programs indicates that many instructions in localized areas of a program are executed repeatedly during some period of time, while the others are accessed relatively less frequently. These instructions may be the ones in a loop, nested loop, or few procedures calling each other repeatedly. This is called locality of reference. Means locality of reference means the tendency of the computer program to access the instructions whose addresses are near one another. So here, in case of loops, in program control processing unit, repeatedly refers to the set of instruction that constitute the loop. So repeatedly it will be executing. For example, for loop, while loop, and nested loop. In case of subroutine calls, what happens every time the set of instructions are fetched from the memory. So that concept we call locality of reference. There are two types of locality of reference. One is temporal locality of reference and spatial locality of reference. Temporal locality of reference means recently executed instruction is likely to be executed again very soon. And spatial means instructions with addresses close to a recently instruction are likely to be executed soon. What that mean? So temporal locality, it is in terms of time. So if an item is referenced, it will tend to be referenced again soon. For example, code and variables in loops. So it keeps recently accessed data closer to the processor. So here temporal locality means the current data or instruction which is being fetched, which is being fetched, may be needed soon. So we should store that data or instruction in the cache memory so that we can avoid again searching in the main memory for the same data. So that is a temporal locality. Spatial locality means if an item is referenced, nearby items tend to be referenced soon. For example, scanning an array. So for example, in an array, if one element is accessed, that means the element near to that element also it's going to referenced soon. So here move contiguous blocks closer to the processor. So what we can do, the array element which are close to the currently referenced item can be bring to the processor. So spatial locality means the instructions or data near to the current memory location which is just now may be needed soon in the near future. So this is slightly different from the temporal locality. So here the spatial locality is nothing but locality in terms of space. The items which are near to the referenced item will be referenced soon. So these are the two types of locality of reference. So next we'll discuss about cache memory. So what is cache? So as we discussed, a cache memory is a very high speed memory used to increase the speed of program by making current program and data available to the processor or CPU at a rapid rate. So here the access time to the cache memory is less compared to main memory. So it contains a copy of the portions of the main memory. So cache will be having a portion of main memory which is going to be referenced by the processor in the future. So here the processor issues a read request. A block of words is transferred from the main memory to the cache, one word at a time. Subsequent references to the data in this block of words are found in the cache. At any given time, only some blocks in the main memory are held in the cache. Which blocks in the main memory are in the cache is determined by a mapping function. When the cache is full and a block of words needs to be transferred from the main memory, some block of words in the cache must be replaced. This is determined by a replacement algorithm. So the replacement algorithm is one which is going to replace the memory block in the cache memory with a new block of data from the main memory. So existence of a cache is transparent to the processor. The processor issues a read and write request in the same manner. If the data is in the cache, it is called a read or write hit. Means the data is obtained from the cache. When the processor wants to read a data and that data is available in the cache, then it is called read hit. So write hit means if it is able to do a successful write operation, then it is a write hit. Cache has a replica of the contents of the main memory. So contents of the cache and the main memory may be updated simultaneously. This is the write through protocol. So in the write hit, if the content of the cache and main memory at the same time, if it is modified or updated, so that is a write hit. So that will be done by using a protocol called write through protocol. So another write hit in terms of updating the contents of the cache and mark it as a updated by setting a bit known as the dirty bit or modified bit. Then the later the content of the main memory are updated when this block is replaced. So this is called write back or copy back. So in this second approach, first the contents of the cache will be modified and it will set that modified bit as a dirty bit or modified. Then later the content of the main memory are updated when this block is replayed. Okay, so that is done by using a write back or back protocol. So actually this copy back protocol is used to overcome the one of the disadvantage of write through protocol, because in the write through protocol when the CPU updates the update the contents in the cache and main memory simultaneously, it will take much time. It will take several clock cycles to update these data in simultaneously in main memory. So it will degrade the overall processor performance. So it will affect the processor performance. So to overcome that, so we can use a copy back protocol. If the data is not present in the cache, then it is a read miss or write miss. So if the when the processor wants to fetch a data from the for in the cache memory, if that data is not there, then it is a read miss. The same way, when the processor is not able to perform a write operation in the in memory, then that is a write miss. So how to overcome this read miss and write miss? So read miss, block of words containing this requested word is transferred from the memory. So if that data is not there in the cache memory, then those words should be transferred from the main memory. After the block is transferred, the desired word is forwarded to the processor. The desired word may also be forwarded to the processor as soon as it is transferred without waiting for the entire block to be transferred. This is called load through or early restart. So what happens when the data, one particular word is not there in the cache, the entire block of those words will be transferred from the main memory. So here the processor won't wait until all entire block of they should be transferred or copied to the memory. So instead of when that desired word is forwarded, then that will be immediately it will forward it or when the desired word is copied to the cache, immediately that word will be forwarded to the processor. So until without waiting for the entire block to be transferred to the cache memory. So that is a early restart plot through protocol. Write miss. Write through protocol is used when the content of the main memory are updated directly. If write back protocol is used, the block containing the addressed word is first brought into the cache. The desired word is overwritten with new information. Then what is a valid bit? A bit called as a valid bit is provided for each block. That means if the block contains a valid data, then the bit is set to 1, else it is 0. If it is, means the block is having a valid data, means the value, the bit valid bit value will be 1, otherwise it is 0. Valid bits are set to 0 when the power is just turned on. When a block is loaded into the cache for the first time, the valid bit is set to 1. So when the first time that block is referred by the processor, then the value becomes 1. Data transfers between main memory and disk occur directly by passing the cache. When the data on a disk changes, the main memory block is also. However, if the data is also resident in the cache, then the valid bit is set to 0. What happens if the data in the disk and cache memory changes and the write back protocol is being used? In this case, the data in the cache may also have changed and is indicated by the dirty bit. The copies of the data in the cache and the main memory are different. This is called cache coherence problem. So cache coherence problem means the data in the cache and main memory are two different values. So these are not, means both are not having the same value, then that is called cache coherence problem. One option is to force a write back before the main memory is updated from the disk by using a write back protocol. Next, we'll discuss about mapping function. Mapping functions determine how memory blocks are placed in the cache. So, as we discussed, the cache memory is a very small memory. So, it will contain a small portion of the memory, not the entire memory or entire storage of the main memory. It will have a small portion of the main memory block. So we need to like based on the mapping function, we need to place few blocks in the cache memory. So cache mapping is a technique by which the contents of the main memory are brought into the cache memory. So mapping technique, uh, it is the one which will bring the main memory blocks into the cache memory. So to explain these mapping concepts, we will take a simple processor example. So in this example, the cache consisting of 128 blocks of 16 words each, means one block can store 16 words. Total size of the cache becomes 2048 words, can store up to 2048 words. Main memory is addressable by a 16-bit address. Main memory has 64K words. Main memory has 4K blocks of 16 words each. So here you can see the difference, the main memory and cache memory storage difference. So here it is having 4K blocks. Okay, 4 into 1024 blocks, that is 4096 blocks. Okay, the cache is consisting only 128 blocks, and each block, each means block in the cache memory and main memory, it stores 16 words. So this is the example we are taking to explain these mapping techniques. So there are three mapping functions or mapping techniques. One is direct mapping, associative mapping, and set associative mapping. So these are the important points to be noted. So main memory is divided into equal size partitions called as blocks or frames. Cache memory is divided into partitions having same size as that of block called as lines. During cache mapping, a block of memory is simply copied to the cache and the block is not actually brought from the main memory. A copy of data from the main memory is stored in the cache, the entire block. So we'll discuss what is direct mapping. So in direct mapping, a particular block of main memory can map only to a particular line of cache. The line number of cache to which a particular block can map is given by this. So how to find out which memory block should go to the which cache line? So the cache line number is equal to main memory block address modulo function number of lines in cache. So this is the formula we use to find out the cache line. So to which cache line the memory block should be mapped. So here this is a small memory block example we have taken. So which is the cache memory is having 4 blocks and the main memory is having some 9 blocks, okay, 0 to 8. So here how to apply this modulo function. So memory block address 0 mod 4. 4 is nothing but total number of lines in the cache, okay, total number of blocks. So 4. So 0 mod 4 division operation, the remainder is the answer. So here the remainder is 0. So that means this block will go to the block cache block 0. Then 1 mod 4, the remainder will be 1. The block 1 will go to block 1 of cache. Then 2 mod 4, 2 remainder, it will go to the cache block 2. Block 3, 3 mod 4. So again it will go to block 3. So here again from block 4 will start from 0 because the cache can have only 4 blocks. So again from here it will start from 0. Again 0 mod 4, 1 4, 2 mod 4, 3 mod 4, like that. Again the same blocks will go to the directly it will go to the same cache blocks in the cache memory respectively. So this is the textbook diagram. So here as per our example, simple processor example, we have 4096 blocks of main memory and 128 blocks of cache memory. So same, so block 0 will go to the block 0 in the cache memory. Block 1 will go to the block the cache memory. So here the same way. So block 0, then block 128. So block 0 to block 127, that is nothing but totally 128 blocks. So next after that 128 blocks, whatever is coming, again it will start from block 0 of the cache memory. Okay, so again here, so from 128 to block 255, again that is the next set of blocks will go to the main memory blocks of 128 blocks. Then again from block 256 to the next 128 blocks will go to the memory block. So like this, the block of main memory is directly mapped into the cache memory lines. So in the direct memory, block J of the main memory maps to J modulo 128 of the cache because total blocks in the cache memory is 128. So 0 maps to 0, again 129 maps to 1. I said, so block 0 to 127 will map to block 0 to 127 cache memory. Again block 128. Okay, so block 128 means in general it is block 129th block. Okay, we are starting from block 0. So block 128 it will again go to block 0 and 129 will go to block 1. So like this it is directly mapped into the cache memory. So more than one memory block is mapped onto the same position in the cache. So here block 0 will have block 0, then block 128, then block 256, like that. So many memory blocks will go to block 0 of the cache memory. So there is a uh, condition arise that is called contention problem. Okay, so what happens if the block 0 in the cache line it is empty and we want to bring block 129 into cache memory, but here the block block 1 is full, but still we cannot map this block 129 into block 0. Okay, because it is directly mapped. So block 129 it must go to block 1 only. We cannot place this in block 0 which is empty. So that is a contention problem. To resolve the contention by allowing new block to replace the old block, leading to a trivial replacement algorithm, because multiple memory blocks we need to copy into block 0, right? So already if the block 0 data is there, then we cannot place block 128. So that is a contention. Here the memory address is divided into 3 fields. Low order 4 bits determine one of the 16 words in a block. So this 4 bit will represent the words in the particular block. Then a new block is brought into cache The next 7 bits determine which cache block this new block is placed in. The block number will be there in this 7 bit. Then high order 5 bits determine which of the possible 32 blocks is currently present in the cache. These are tagged. So 5 is used to take the means the block number to identify the block. So this is a main memory address format. So totally 16 bit. So 7 plus 5 plus 4, 16 bit the address is used. So this direct mapping technique, it is very simple to implement but not very flexible. So this is not flexible due to the contention problem. The next technique is associative mapping. So here any block from main memory can be put in any cache. So no direct mapping is there. It is completely flexible technique, because here any block can go to any block in the cache memory. So here the main memory block can be placed into any cache position. Memory address is divided into two fields. Low order 4 bits identify the words within a block, and high order 12 bits or tag bits identify a memory block when it is resident in the cache. So this is the main memory address form. So it is flexible and uses cache space efficiently. Replacement algorithm can be used to replace an existing block in the is full. Cost is higher than direct mapped cache because of the need to search all 128 patterns to determine whether a given block is cache. So cost wise it is bit expensive compared to direct mapping, because when the processor wants to search a data in this cache memory, it has to search in all the 128 blocks, because the data from the main memory block can go to any block in the cache memory. So processor has to search in all 128 blocks. So the cost is bit high compared to direct mapping. The third method is set associative mapping. So here the cache blocks will be assigned to a set, means the number of cache blocks will be assigned to a group, which is called a set. So here in this example you can see we are having a set which includes two cache lines. This consists of two cache block lines. So how to find out the number of cache blocks per set? So that we use n by s. The n is nothing but total number of cache blocks in the cache memory divided by set, the number of sets we want to. So that is a k comparisons required for search. So here the the processor can search in this k number of sets instead of searching in all the memory cache memory block lines. It can search only the uh, k number of sets in the cache memory. Cache lines are grouped into sets where each set contains k number of lines. Particular block of main memory can map only one particular set of the cache. However, within that set, the memory block can map any cache line that is freely available. The set of the cache to which a particular block of the main memory can map is given by cache set number, main memory block number, address modulo number of sets in a cache. So to find out which memory block from the main memory go to the cache, that particular set number, so that we use here this formula, this modulo function. So here instead of number of cache line, we use number of sets in a cache. So here so blocks of caches are grouped into sets. So here we can see, so here what we are using is we are mapping two memory blocks into one set. Okay, so there will be two blocks in one set. So mapping function allows a block of the main memory to reside in any block of specific set. So block 0 and block 1 of main memory can go to anywhere. So anywhere, any blocks in the cache memory, either it can go to block 0 or block 1. So that means block 0 can either go to block 0 or block 1 of the cache. The same way, block 1 can either go to block 0 or block 1. So that is a associative mapping. Okay, so here the set associative mapping, it is a combination of direct and associative mapping. So why direct mapping means here the block 0 and block 1, it should go to the set 0. So this set 0 blocks only. Okay, so that is nothing but direct mapping. But within this set, these two blocks can go in any blocks in the cache memory. As I said, block 0 can go to block 0 or block 1 line in the cache memory. So that is nothing but associative mapping. So the set associative mapping, it is a combination of direct mapping as well as associative mapping. So here we divide the cache into 64 sets because we have a 128 blocks and 2 blocks in a set. So 128 divided by 2, n by s. So that is nothing but 64 sets which with the 2 blocks per set. So from set 0 to set 63, that is nothing but totally 64 sets. Memory blocks 0, 64, 128, etc. map to block 0 and they can occupy either of the two positions. That means block 0, block 1. Set associative mapping, as I said, it is combination of direct and associative mapping. Number of blocks per set is a design parameter. One extreme is to have all the blocks in one set requiring no set bits, fully associative mapping. So one design parameter is that to have all the blocks in one set. All the blocks in a one set, that is nothing, again it is a fully associative mapping. Again the processor had to search in all the blocks in a one set. Other extreme is to have one block per set is same as direct map. So again if we place one block in one set, then that is nothing but again it is a direct mapping technique. So these are the two design parameters set associative. So next we'll discuss about replacement algorithms. So replacement algorithms are used when there are no available space in a cache in which to place a data. So then these replacement algorithm will bring a new memory block cache memory by replacing the memory means cache block in the cache memory. There are four of the most common cache replacement algorithm which are discussed below. Least recently used LRU algorithm. The LRU algorithm selects for replacement the item that has been least recently used by the CPU. First in, first out means this algorithm selects for replacement the item that has been in the cache from the longest. The blocks which are brought into the cache in the first time. Then least frequently used LFU. The LFU algorithm selects for replacement the item that has been least frequently used by the CPU. Then the next category is random algorithm which selects for a random replacement the items randomly. So here the random algorithm is it will not see whether it is frequently used or recently used or first time brought into the cache. It will just select randomly in the randomly it selects the cache. It replaces with the new blocks from the main memory. So these are the very commonly used replacement algorithms of cache memory. So one of the popular replacement algorithm is LRU, that is least recently used algorithm. The cache controller, so in this algorithm, the cache controller must track references to all blocks as computation proceeds. So we need to find out which block is least recently used. For that, the cache controller uses a special computation to find out which block is least least recently used. Suppose it is required to track the LRU block of a 4 block set in a set associative cache. A 2-bit counter can be used for each block. So if 2-bit counter means 2-bit value. So we can form 4 different value from 2 bits value, right? That is 0 0 that represents 0, 0 1 which represent 1 value 1, then 1 0 which represent value 2, then 1 1 represent value 3. So we can have 4 different value from 2-bit counter. So when a hit occurs, the counter of the block that is referenced is set to 0. Whenever a hit occurs, means successful operation fetching operation is done from the cache, then that will be set to 0. So counters with values originally lower than the referenced one are incremented by 1 and all other remains changed. If any particular block which is not referenced, that will be incremented by 1. So when there is a hit occurs, the block will value set to 0 by default. But all other which is not referenced, that value will be incremented by 1. The counter associated with the new block loaded from the main memory is set to 0. Again, when new block comes to the cache memory, then also it is set to 0. And the values of all other counters are increased by 1. When a miss occurs and the set is full, the block with the counter value 3 is removed. Means the 3 is the maximum value for this 2-bit counter. So when the memory block wants to replace a new value into the cache memory, it will check all the block value is having the maximum value 3. So that value that means it is not referenced for a long period of time. That is least recently used or least recently used. So then those block will be removed and new block will be placed in that particular location. So then the other 3 block counters are incremented by 1. It can be easily verified that counter values of occupied blocks are always distinct. The LRU algorithm has been used extensively. Although it performs well for many access patterns, it can lead to poor performance in some cases. For example, it produces disappointing results when accesses are made to sequential elements of an array that is slightly too large to fit into the cache. Performance of the LRU algorithm can be improved by introducing a small amount of randomness in deciding which block to replace. So this is important points with respect to LRU algorithm. So that's all we discussed in this today's session. So in today's session we discussed about read size cost with respect to memory hierarchies, cache memory, and briefly discussed the 3 mapping techniques, that is direct mapping, associative mapping, and set association.